The dataset consists of a set of images where each image has been acquired at a binding energy. So this first set of images represent carbon 1s, and if I overlay them in the active tile, bring up the image processing window and go to the color scales, there's an option that lets me look at the signal from a specific pixel in this case, and you can see this noise is a feature of individual pixels. If I move around and set the position, I can see spectra here. Let me first introduce a different color for the display, and that will just make it a little easier to see the spectrum in this form. And if I want to, I can sum pixels in a box. So I've just drawn out a box, and you can now see that within this box, if I sum all of these pixels and assign an intensity based on the energy that's associated with the images that are displayed, overlaid in this tile, then we get a spectrum, and the spectrum is that of a carbon 1s, and we're interested in working out the changes, the peak shape changes here in the background compared to the intensity of the peak itself. So that's the carbon 1s. We can also overlay the oxygen 1s, and again here's a classical shape for oxygen 1s, and similarly this is a silicon 2p, and these represent signal from a substrate which is silicon dioxide. The act of summing the pixels is providing an average spectrum, and hence we can see significant features in these data. If rather than using the average spectrum we look at the individual pixels, it would be hard pressed to work out the relationship between the background and the peak itself based on these data from individual pixels, and nevertheless that is exactly what we're going to try and do. But the first thing we need to do is to use an option on the image quantification window, and what I will do is select all the images, and we will perform outlier filtering on all of these images using a 70% threshold, and we'll iterate 5 times to adjust these pixel intensities. And after doing these 5 iterations of the outlier filter, you can already see that the spectra at pixels are now looking much more in tune with what we need to work out a peak area and a background. So that's the first step. So we'll copy all of these images to a new experiment frame, and we'll take process data only, and this allows us to do some further processing without fear of undoing at some point the processing that's just been done by the outlier filter. So the processing that we're going to try and do is we would like to look at the variation within this data set by doing an optimum scaled singular value decomposition into abstract factors, and the abstract factors will give us the variation in the data ranked by in principal components. And when we understand how many factors we've got, we can then apply the same principle again, but apply it with a specified number of abstract factors and reproduce the data to effectively remove the noise from what's remaining. So as I scan down here, I'm looking for evidence of shape information. I've calculated 20 abstract factors. I'm now looking at the 7th, 8th, 9th and the 10th. All of those look like noise pretty much to me, so what we'll do is we'll reproduce these data, and first I need to set them back to the original state. This is where we've maintained the outlier filter processing, because this is what the PCA is acting on, and I'm going to specify 10 abstract factors, and I'm going to predict using 10 optimum scaled abstract factors on the dataset. And having completed this reproduction step. That is to say, we've used 10 vectors calculated from the principal components of the original data set, and we've reconstructed each and every image using the 10 abstract factors. The spectra look really quite good. So if I move around again, you can see that we're at individual pixels. We've now got quite a reasonable spectrum at a pixel. And there's an example of where you can see the background has raised as a consequence of a different position on this sample, and that's what we're interested in. So let's create from these a set of spectra, and from these spectra we're going to assign regions and extract images based on these regions. So I've brought up the quantification parameters dialog window, and I'm going to start off very much as I did with spectra. That is to say, I first of all define the polymer Tougaard background. I'm going to use U3 using the parameters that were introduced by the polymer. I'm going to that's the polymer background. I'm going to increase the number of points used in the average width. Again, I've got to just set this to binding energy, and then I'm going to go for 3, 1, 2. This is peak position is 282, so I've gone for 30 EV higher, and also I'm going to go for the same interval that I used but shifted, because these data have been shifted. Charge correction hasn't been performed, so they're shifted, and hence I've used an interval from 312 to 267, a U3 Tougaard background, and the idea is that we're going to calculate this B parameter for each spectrum, and we want to record it. So the next thing I'm going to do is I'm going to put in cross section underscore B for the tag field, because I'm going to use the tag mechanism to extract the information of interest when I calculate my images from these spectra. And the next thing I need is to measure the area, so I'm going to put a skip background and adjust the region so that this second region works out the area above the existing background. Hence I've used skip rather than specify a background to calculate over this interval. It's using the U3 Tougaard background to work out the area of these peaks, and I need to say this is raw area CPS EV, and I'm going to propagate that to all of these carbon 1s VAMAS blocks. And I want to make this very specific, that we're going to call this one B1. This was AP. I'll propagate and then calculate the images. So now we have two images, one of the B1 parameter and one where is the area of the carbon peak. So we can see that most likely we've got more carbon in certain places on this sample, and what we're going to do now is work out a film thickness based on these. As part of the calculation of the film thickness, we need an estimate for the bulk intensity for a ppx film over silicon, and although in this case we don't actually have the data in that precise form, what we can do is we can estimate the film thickness by summing these images to get a total intensity image that will give us an estimate of the the way the intensity varies as a function of position in these images, and we'll do that by going to the Test Data tab, and we will, having overlaid, as you can see by the red boxes, that all of these images are overlaid in this active tile. If I say sum, I then have a new VAMAS block at the bottom of the file which represents the sum over all of these images. I'll just copy that through to a new experiment frame in the process form, and I'll do the same operation on this image as was performed for the data itself, and I think I'll copy that again in the process form. So I've got an image which I will now call sum of all images, and let me just remove the one that I'm not going to use. So I've deleted that one, and this is the one that I'm going to use. Now this is going to provide an example of how you can manipulate images using the image calculator. So there's a window I can bring up, and this image is 128 by 128. So let me just introduce a calculation of the number of pixels, and I'm going to divide that by a scale factor which will give me, if I calculate a normalized image, if I multiply the normalized image by the scale factor, I will get intensities within the image that are characteristic of the film thickness from a bulk material. And this is not precise. This is just an example of how the calculator can be used to generate another image from an image that you already have, and we'll use it as an approximation in the calculation that will follow. So this is the equivalent of AHP in the formula, and what I need to do is find the pair of images that I calculated. So I'm selecting these two first, and there's a reason I'm selecting them first is because I want them to appear in the new file that I'm just about to create in the order I selected them. So you can see it goes B1, AP, and the sum of the images, and I'm putting these all in the same file. So when I display the VAMAS block indices, which is the strings that are used within the calculator, I can then work out which VAMAS block I need to apply which operation to. So let's use this calculator on the VAMAS info page, and I'm going to use the formula that's very similar to the one that was used in the custom report. It's not quite the same, it's slightly different. You have definitions just like in the custom report that represent these less than, greater than strings, but they appear as you would see in the custom report, but when it comes to actually defining a calculation, it's just a single line. There's no need to put in a name anymore. It's just the formula that appears. So throughout this file I've got sets of pairs of definitions and values, and then ultimately I combine them all in this term here to give me a formula that will be quite complex when it's seen in the final result, but the principle that was used in the custom report is also applied here, that you simplify the calculation in terms of its definition by using these types of strings. And in particular, that's my AHP that I've got in this formula. I've got a number. I'm not going to use a number. I've now got a VAMAS block, which I'm going to say is VB2, so this summed one that I scaled previously, and I'm going to use that instead of the absolute value that would have been used in a spectrum. This is over a field of view, so I have to try and use the image to allow for variation of intensity as a function of position. And then I'm going to say apply, and you can see that the B1 is this VB0, and AP will appear here as VB1, and then the dividing by the bulk area, that's coming from the VB2, which I've specified here. So when I press OK, a calculation is performed and we get an estimate for the film thickness. So let's just give that a name. We'll call that depth nanometers. So this is the estimate for the thickness of this carbon layer on top of the silicon dioxide. So you can see here you've got islands of thicker carbon and valleys of contamination.